All right, thanks for the great presentation, Adar. So let's see if there are any questions. Okay, so I see a question in the Slack from Siyuan Chai. Great work and thanks for the presentation. I have two questions. First, in your paper, you compare the memory consumption between the normal Cuckoo Trie and the Cuckoo Trie with resizing. I think a Cuckoo Trie with resizing can give you a lower load factor and therefore a lower chance of hash collision. What about its performance compared with the normal Cuckoo Trie?
We tested a few load factors, and it's true that when the load factor is lower, the Cuckoo Trie is faster, but it is not much faster. So the graphs that we saw in the presentation are pretty representative, I'll say. Maybe when you do resizing, you'll have, say, 10% faster operations, but no more.
Okay, got it. I also have another question. So I think you mentioned in the presentation that for workload with the very long common prefix, the Cuckoo Trie actually has a performance. I mean, the performance is not very good. I'm just wondering if we can try to cache some of those common long patterns so that there might be some performance gain, because you may need to frequently traverse through the trie.
So if you have just a few long prefixes and each prefix has many keys under it, then it's true. Actually, the processor will automatically cache these nodes in its internal cache. But in that Amazon dataset, we had many such long prefixes, and each prefix was shared, say, between 5 or 10 keys. So the caching isn't very effective.
Okay, got it. Thank you.
All right, I see more questions. Sujana, you want to ask? Sujana.
Yeah, great work and presentation. So I had a quick question about the performance of Cuckoo Trie on update and delete operations, and if you were able to do updates and deletes in, I mean, atomically, like given you have like two data structures now to manage, was it like more complex, or does Cuckoo Trie support it?
So we did not implement deletions because we didn't measure them in the paper, but it is possible to perform atomic deletions, and all the graphs that we saw for inserts and for lookups are for atomic operations. So everything is either atomically implemented or possible to implement atomically.
Mm-hmm. And how was the performance of Cuckoo Trie on updates? Like, was it slower than like normal?
Well, updates are similar to lookups, because an update is just a lookup, and then you just write to the current key the new value. So it is more like a lookup than an insert.
Okay, all right, thank you. That answers my question.
Good.
Okay, we also had a question from Yao. John.
Yeah, so my question is mostly about, the trie gives you uniform node size. Have you considered varying that particular size? Like instead of doing 1 byte at a time, have you tried varying that to be maybe more than 1 byte, and then see if there is a trade-off basically between the per node size and the number of memory lookups?
Well, there is a trade-off, and it's detailed in our paper. Basically, we chose the node size such that each bucket of the hash table fits in a cache line of the processor, so that each hash lookup is only reads one cache line. You can have larger nodes, then you'll have less memory accesses, but each will be more than one cache line.
And did that, when you tested, did that give a performance difference or memory size difference deviating from that the value you chose?
So yes, generally the larger the node is, you have more performance, but also more memory usage. So we chose some sweet spot in between.
Thanks.
I think Sudarshan had a question.
Hi. Sorry. Great work. Really interesting talk. With increase in memory with the hash table, the footprint in the processor cache L1, L2, and L3 is probably also going to increase. So I'm just curious, like, did you kind of measure the impact of, like, is there an increase in the processor cache utilization, and is that incurring higher misses? And for memory parallelism, prefetching plays a very key role. So I'm just curious if you had seen some effects on prefetches.
So in fact, for your second question, our implementation uses prefetches to make the memory accesses parallel. The CPU cannot perform it by itself. So yes, they are a key ingredient of the data structure. And for the caches, all the benchmarks we did were with very large data sets. So the cache holds maybe the first 2 or 3 levels of the trie, and all the rest is always brought from RAM.
Thank you.
All right, any other questions for Adar? I see someone raise their hand. Mike?
Yep. Yeah, I'm just curious, is there any risk in your design that somehow your data structure consumes too much memory bandwidth that affects the rest of the application?
So we tested that, and we think that at least on our server, it is not the case. Even when we use all the cores and run full power Cuckoo Trie, it does not use the full available memory bandwidth. If you have other very bandwidth heavy applications, it might affect them, but it does not use the full bandwidth.
Thank you.
Yeah, good question, yeah. Anyone else? I'm just trying to monitor all the places where questions can come. Okay, well, if there are no more questions, we'll also have a chance at the end of the session. We'll have a panel with all the authors, so you can also ask stuff then. Okay, so I think we can go to the next paper. Thank you.
Right, thank you very much for the great talk. So Adam and Adar, if you're here, if you could start your video, that'd be fantastic. As a reminder, if you want to ask your question live, then please raise your hand and I will promote you and you can ask it live, or you can ask it in the thread that is for the paper in the Slack channel. So let me do a quick scan. I don't currently see, oh, I see one question. You should be able to talk now.
Hello, can you hear me?
There's a lot of echo.
Sorry, now. Wait a minute. Now can you hear me?
Yes, perfectly.
Okay, thank you. Thanks for your presentation. And I have a question that since you mentioned that in the easy Cuckoo Trie has worse performance than the other trie-based index. So I want to ask that in what kind of workload Cuckoo Trie will have a better improvement compared with other index.
So I think that the best case for the Cuckoo Trie is when you have a lot of keys where each key has a pretty short unique prefix. So if I give you, say, the 5 first bytes of a key, then you have only one key that starts with those 5 bytes. Or you don't have to look far into the key to find it uniquely. That's when the Cuckoo trie is the fastest.
Okay, so it means that long common prefix make it worse, and it prefers short common prefix.
Yes,
right.
the keys themselves can be long, but the prefix that identifies them uniquely should be short.
Okay, I see. Thank you.
Thank you very much. So we have a question in the Slack by Hassan Wassel. Using MLP incurs many simultaneous memory accesses. What does that mean for memory bandwidth usage?
So what we found, at least on our server, is that modern CPUs actually have quite a lot of memory bandwidth. So we were able to run 28 parallel threads, all of them performing multiple memory accesses in parallel, all of them running the Cuckoo trie full speed. And the memory could cope with that. So at least when you run just the Cuckoo trie, memory bandwidth is usually not a problem.
All right, do we have any other questions on Zoom? I'm seeing one, and if you could introduce yourself first and turn on your video, that would be fantastic. Wei, I don't think we can hear you right now.
Sorry, am I audible now?
Yes.
Hey, yeah, I'm Wei from NUS. So I'm just wondering, because I see in that you did some benchmarks in Redis. So, and it seems that your benchmarks were generally positive for the Cuckoo trie. So would you consider upstreaming this to Redis as perhaps an option for the implementation of like I can't remember the exact structure it was, but yeah.
So currently I don't consider it because first we didn't implement deletion yet. It is certainly possible to implement it, but we didn't do it yet. And second, our index is faster for some kinds of keys, but for others it is slower. So for a general purpose database such as Redis, I don't know if it is good to have such an index as the default, maybe as a special case.
Thank you.
So Adar, could you say a little bit more on which workloads is the index slower and why?
So it is mostly slower when the trie turns out deep. And that happens when, as we saw in the AZ dataset, when you have long prefixes that are shared between a few keys. Say that, just as we saw. I think all cases where it is slower are boiled down to this kind of workloads.
Not seeing any other questions on Zoom, so I'm going to ask another one, take advantage of this. So this was something that was asked this morning, but I thought it was a really interesting question, which is, have you looked at using the Cuckoo trie for persistent memory indexes?
Well, I didn't look into it, but it might be possible. I really don't know.
Yes, so actually we have another project going on and we're looking into it. Adding crash consistency and seeing the performance characteristics of persistent memory for this type of memory level parallelism using algorithm.
Great, thank you. So I think with that brings us almost to the end. I will virtually thank the speaker and Adam as well. And thank you very much. Looking forward to then was it OSDI 2022 for the NVM version?
Hopefully.
So thank you very much. So we're going to be moving on to the next paper in the session, which is regular sequential